The MSC Irina is 400 meters of solid steel, and fully loaded she weighs over 240,000 tons. Drop a steel bar in water and it sinks instantly, so in this video you will understand exactly why she floats. You will learn how buoyancy works, why ships stay upright, why compartments matter, and the hidden effect that still sinks them. Start with the mistake almost everyone makes, because people assume floating depends on what an object is actually made of. Does not, because floating depends on shape, and shape is the single most important word in this entire video. Steel is roughly 8 times denser than water, so a solid block of it drops straight down to the seabed. But a ship is not a block of steel. It is a thin steel skin wrapped around an enormous volume of air. Weigh the steel, the engines, the cargo, and all that trapped air together. Then divide it by the total volume. The answer is the average density. And for a loaded container ship, it stays comfortably below the density of water. That is the whole trick. The ship is mostly empty space, and empty space is what keeps the steel up. Now look at what the water itself is doing, because water pressure increases the deeper you go beneath the surface. The bottom of the hull sits deeper than the sides, so the water pushing up is stronger than the water pushing down. That difference in pressure is buoyancy, and it is not magic, it is simply the sea squeezing the hull from below. As the hull settles lower, it shoves water aside, and every single ton of water it moves pushes back upward. The ship keeps sinking until the weight of the water pushed aside exactly equals the weight of the ship itself. At that exact moment, the two forces cancel out. The ship stops sinking, and it just floats there perfectly balanced. Archimedes worked this out over 2,000 years ago, and every ship afloat today still obeys exactly that same rule. So MSC Irina, fully loaded, must push aside 250,000 tons of seawater before she stops sinking. Loading containers onto her does not fight buoyancy, it just makes her settle a few meters deeper into the sea. She is 61 meters wide and 400 meters long, spreading her weight across a gigantic footprint of displaced water. Widen a hull, and it displaces far more water for every meter it sinks, so it barely needs to sink. There is a marking painted on the side of every cargo ship that tells you exactly how deep it may sit. It is called the Plimsoll line, and if the water rises above it, that ship is legally and dangerously overloaded. Before 1876, owners could overload ships freely, and crews drowned so often that the public simply called them coffin ships. A British MP named Samuel Plimsoll forced through the Merchant Shipping Act, and that line has been mandatory ever since. The marks also change with water, because seawater is denser than fresh water, and therefore pushes back a little harder. A ship floats higher in the ocean and sinks lower in a river, so the line has separate marks for each. Floating is only half of the problem, because a ship that floats but tips over is still a total disaster. Two invisible points decide this: the center of gravity, where the ship's weight acts, and the center of buoyancy below it. The center of buoyancy is the middle of the underwater hull shape, where all of that upward push effectively acts. When the ship rolls, the underwater shape changes, so the center of buoyancy slides sideways toward the lower side of the hull. Now the upward push and the downward weight are no longer aligned, and together they twist the ship back upright. That twisting force is called the righting moment, and it is the reason a ship rolls in waves without capsizing. Here is the detail most people miss. An empty ship is actually far less stable than a properly loaded one. Empty, she rides high, with her weight sitting up in the hull, and high weight makes her want to roll. So ships pump thousands of tons of seawater into ballast tanks low in the hull to push the weight down. The cargo itself does the same job, which is why heavy containers always go low and light ones go high. So the ship floats and stays upright, but what happens the moment the sea actually gets inside the hull itself? A hole in the hull is not automatically fatal, because the inside of a modern ship is not one open space. Steel walls called bulkheads divide the hull into sealed watertight compartments, running from the bottom right up through the ship. Flood one compartment and the ship settles slightly, but the other compartments still hold enough trapped air to keep her afloat. Modern rules force ships to survive flooding in a set number of compartments, and warships are built even tougher than that. Titanic had 16 of these watertight compartments, and the newspapers happily called her practically unsinkable because of that very design. She could float with any 4 of her forward compartments completely flooded, which was a genuinely advanced standard for 1912. But the bulkheads did not reach the top of the ship. They stopped only a few decks above the waterline. So think of an ice cube tray that has walls between the sections, but no lid across the top of it. Tilt that tray, and the water simply spills over each wall into the next section, filling one compartment after another. The iceberg opened her first 6 compartments, the bow dipped down, and water cascaded backwards over every bulkhead in turn. The compartments worked exactly as designed, but the design itself was simply never meant for damage on that kind of scale. Today, bulkheads run far higher, doors close automatically, and most large ships carry a full double hull wrapped around them. So if buoyancy is that strong and compartments are that good, how do modern ships still end up sinking today? The truth is, most of them do not sink because they lose buoyancy. They capsize because they lose stability first. The single biggest hidden killer in all of ship engineering has a strangely gentle name. It is the free surface effect. Water that is loose inside a ship does not sit still. It slides downhill every single time the ship rolls. That sliding water shifts weight to the low side exactly when the ship is trying to push itself back upright. It is like carrying a wide tray of soup, because the liquid keeps running to whichever side is tilting down. So the righting moment shrinks, the roll gets worse, more water slides across, and the ship rolls even further still. In 1987, the ferry Herald of Free Enterprise left the port of Zeebrugge with her bow doors left wide open. Seawater washed across her flat open car deck, sloshed hard to one side, and she capsized in about 90 seconds. 193 people died, and she never truly lost buoyancy at all. She simply lost her balance. That is why ballast tanks are kept either completely full or completely empty, and never ever left carelessly half-filled. Tanks are also divided by internal baffles, because narrowing the water's path dramatically reduces how far it can actually slide. The other classic killers are simple: overloading past the Plimsoll line, and cargo that breaks loose and shifts hard sideways. So a giant steel ship floats because it is mostly air, and it displaces exactly its own weight in water. It stays upright because its shape pushes back whenever it rolls, and it survives damage because it is carefully compartmented. The steel was never really the problem, and the sea was never really trying to sink it in the first place.